So let's get started with 2.2, Introduction to Polynomial Functions. A quadratic is a polynomial function. So everything that we have learned about polynomials go into it. So about quadratic still fits in if it's a quadratic. We're going to add some things to it. Everything we know is going to jive with what we're about to talk about. But now this thing can be either a third degree or fourth degree, and we're going to kind of talk to them in general terms. Okay, so that's the 2.2. And what we're going to do is we're going to start out, we're going to talk about the end behavior of a polynomial function. We're going to recognize this. I'm going to show you from what our previous knowledge is. We're going to do some zeros. Factoring, this is what this is, identifying zeros, just like if we could factor a quadratic, what would be the zeros or the x-intercepts? And then multiplicities, that's just the power of that factor. And we'll learn how to use this information that we've got to sketch a polynomial function. And this intermediate value theorem, it just says that if I've got a continuous function, and if I know the two pieces that it's going through, one above the x-axis, one below the x-axis, I've got to cut the x-axis. If it's continuous, polynomials are continuous. Okay, all polynomials are continuous. So what is this end behavior stuff? Okay, so it's got all of these things, and we got to know what all of this stuff is. So this is basically what we're talking about, and I want to go over here to my side to make sense out of this and put this into perspective. Okay, so let's talk about the two polynomials that we already know, the base polynomials. So I'm going to sketch this out. Okay, so here's my x, here's my y, and I've got that base function of f of x equals x squared is what we did, and I've been emphasizing that this is all of the powers. This may be tightened up for n even. 2, 4, 6, 8. So if this was an x to the fourth, that's a fourth degree, a sixth degree polynomial, a eighth degree polynomial. They're always going to look like this, and this is the end behavior. Okay, so end behavior is what it does at these ends. Okay, what does this do, and what does that do? Okay, and I want you to know this graph for all of these. This is the end behavior. So I've got a little guy that's walking out on my x-axis, and he's walking out to infinity. Okay, so as these x numbers, that little guy goes to plus infinity, he's going to look up or down and say, what is my y values doing? And y is just going to plus infinity. Okay, so for x to the n, this is the end behavior. As x gets larger, y is just going to get larger. Okay, what about if this guy is walking this way? Got a guy out here walking, and he's going to at negative infinity. So here, he's going to negative infinity. For this function, he's looking up, and again, y is going to plus infinity. Remember, we've got here is going to plus infinity, just like a number line. Here's negative infinity, plus infinity this way, and then minus infinity that way. Okay? That is the end behavior. That's what it's telling you here. Let me slide this over, and in these words. Okay, so this is what this means. This notation, x goes to infinity, x approaches infinity, goes to infinity. Okay, x becomes infinitely large in the positive direction. Okay, we're getting larger and larger. Okay, as numbers get larger and larger, what's happening? As x goes to negative infinity, that's this piece of it. Okay, so this is x going to infinity. This is x going to negative infinity when he's walking that way. Okay? And now we say f of x goes to infinity. This is the same thing as this piece. So we can say either y or f of x goes to plus infinity, f of x goes to plus infinity. Okay? In a minute, this does not always need to be this way. Okay? So f of x goes to plus infinity means that it's going in a positive direction up. And then if it goes to negative infinity, that means it's going down. For this basic function, for any nth degree polynomial, we're going to talk about this in a minute, it's going to be this very same basic picture. Things are going to happen in between, but at the ends, this is what's going to happen for this. Okay? Positive x to the n even. Okay? So what about, now we know what the transformation g of x is negative f of x is, right? We know what that is. That just flips everything around the x-axis. Okay, so what if I have f of x, the base function, being negative x to the n, and let's pick out one. So this is negative x to the 6. So my n is even. It's going to be the same behavior, except now this picture is going to go like this, right? So now I've got this quick picture that if I do, this is going to go like that, okay? So just from knowing the degree is up, up. That basic one is just up, up. And now if I do a negative, this is going to go as x goes to infinity. Now it's going down. F of x goes to negative infinity. And then as x goes to negative infinity out this way, he's still looking down. F of x goes to negative infinity. We're going to do like this one for the evens. Then we're going to do an odd, but we're going to keep up with this because every time we look at a polynomial and graph it, we're going to say, well, what's the end behavior? What do we need to make happen here? And then the rest of it, we're going to go through some zeros and some y-intercepts. Okay. So here's a general polynomial, right? A to the n, x to the n, a to the n minus 1, n minus 1, a to the n minus 2. So these are just different numbers. So every set of unique numbers would be a unique polynomial, different sketch. Okay. The highest number, this is the degree of the polynomial. That highest degree is the degree, that highest number. Okay. And what happens that this tends to dominate as we get out large numbers. This would be a larger number. So if I was at 100,000, I would be multiplying this number times 100,000 more than this number would be. Okay, so this tends to dominate. Once you get out to large numbers, this tends to dominate, and this dictates the end behavior. So all I have to do is look at the highest power and then determine the end behavior from there. If a sub n, so if n is an even number, a is positive, this is what I get. This is what dominates. If a sub n is negative, and if it's an even power, the n is even, this is what's going to happen. That's the end behavior. Okay, so here's a picture of that. Here is a to n positive. This is up, up. That's the picture up, up. Okay, that's what I'm saying here. We're going up. This is this arrow. On the other side, we're here. So this is from that basic graph that we know when n is even power. For even powers, it's either up, up, or down, down, like over here. And all I have to do is just determine whether an is a positive number or a negative number. And that's what I wrote here. Negative infinity, positive, infinity, positive. Negative infinity as x goes to positive infinity, and then f of x goes to negative infinity as this should be as x goes to negative infinity. They should be switched, but okay. So now let's look at the odds. So this is the basic what we've got going. for n even, a sub n positive, right, positive here. As we go out here, x goes to plus infinity, f of x goes to positive infinity. X goes to negative infinity, f of x goes to positive infinity. Okay, and if this is negative, all of this is just flipped. So this is the only one you have to remember, and just know that it flips. And now as x goes to plus infinity, f of x goes to negative infinity, and then as x goes to negative infinity, f of x goes to negative infinity. He's looking down. Okay, so now let's do the odd versions. Okay, so let's start out with what we know from our previous base functions. We practiced this a lot, identifying these things. That's the one that we have done. Let me make sure you see this there. The x cubed is the one that is presented, and I've been telling you all along that this is the way this thing looks for x to the n, and here n is odd. So 3 is the smallest, 1 is a straight line. If n was 1, that's just a straight line. 3, 5, 7, 9, not divisible by 2. I have a remainder if I try to divide by 2. Okay, that's the basic shape. The higher powers, this thing is going to tighten up a little bit because you got a higher power going here and then a higher power going down here. Okay, but let's look at the basic end behavior. Now this is the end behavior. Again, as my little guy is running out this way and this way, what is he doing? Okay, so as my little guy is walking to infinity, this is the end behavior. As x goes to infinity, here's my little guy walking out here. He's looking up. F of x is going to plus infinity. Okay, but now if he's walking back this way, he's having to look down to get to that tail. As x goes to negative infinity, f of x goes to negative infinity. Okay, so as long as I've got any polynomial, so if I have this polynomial, let's go 10x to the 17th plus 4x to the 16th minus 3x squared plus 1. I don't have to have all of these terms. Some of these could be 0, but that's still that general term. Here I look at the highest power, and this is going to be the end behavior. There's going to be a lot of stuff going on in here, but the end behavior would look like that. Okay? And let's see if we can pick this up on Desmos. Let me drag this down here for just a second. Over here, let me push this out of the way for a second. And if I have, let me get to Desmos. Come on. We're getting there. So I'm just going to type this in real quick of what I had. I had 10x to the 17th plus 4x to the 16th minus 3x squared plus 1. Okay. So notice that this is the 17th, and if I zoom out, a lot of stuff's going on in the middle, but the end behavior as we're going out this way, we're going down, just like this, and then we go up. Okay. And I'll make one change here and watch what happens. If that leading term now goes to, let's go 18, now it's up, up. Even power, positive. If I change this to a negative, then I go down, down. And if I do the 17th, we haven't covered this yet, but now instead of down up, it's going to be up down, odd power with a negative. And that's what I'm going to talk about next, is just flipping this. Okay. So all of this is based on a to the n, whatever this is, being positive. Okay. If I do a negative, so if I've got just a negative version of this, this is just flipped. So a to the n is a negative number. I'm just going to flip this picture, and that's what I get. So all I needed to know was two pictures, the even and the odd for all polynomials, and then if it's negative, I flip both of these things. So here I'm going to write my end behavior as we're going this way now. Now the guy is looking down. F of x is going to negative infinity. Okay. And then as we go this way, as far as we're going this way, this thing is getting bigger. So as x goes to negative infinity, f of x is going to plus infinity. Negative, and then the positive there. Okay. So from my two pictures, x squared, x cubed, I get all of this information, and I just flip it to get the other versions of that. Okay. Okay, so let me continue on. Let's go with our end behavior. I'm going to slide this over here. So here's the a to the n x odd. So this is down, up. So this is kind of, if you picture this, that's that picture, that S kind of going up from down up. And then if you flip this into a negative, then we're going to go down, from up to down. And this is how we express that. Okay. You can remember this picture. Sometimes they're going to ask you for this. Write the end behavior. But when you're sketching, these are the pictures that you're going to kind of mentally start with. Okay. So use the leading term to determine the end behavior of the graph of the function f of x is equal to x to the fifth. X to the fifth. So we're not going to do all the middle stuff, but we're just going to say, where are we starting with? Okay. So I'm going to go to the biggest term. This is the largest term, highest power. So in general, this is a fifth degree polynomial. A fifth degree poly. That's that number there, the fifth degree. Okay, this is odd. 5 is odd. Okay. So I've got an odd degree, something like this. So I'm thinking this picture, okay? The basic one is x cubed, the basic odd picture, okay? And that's the end behavior. So this end behavior, when I start graphing this thing for a real graph later on, I'm going to go out and I'm going to say, okay, we're going to start left to right. I'm going to come from the bottom and I'm going to go up like that. And then at the very end of my graph, I'm going to go up like that. Here and here. That's going to mimic that picture because odd degree, positive. If this was a negative, then I would just flip these things. Okay, so it would be, so if this was negative and then negative, this is the positive, okay, which is what we've got. But if this was negative x to the fifth, this would be the way I would do it. To get me started, then we start filling out information that we knew in here. We need calculus to get our local maxes or mins, but hopefully we're going to be able to do some zeros. We'll factor, set each factor, and then we'll always be able to get a y-intercept. In this case, 0, 0, 0, that y-intercept would be right there. Okay, it would also be an x-intercept. use the leading term to determine the end behavior of the graph of this function. Okay, so this one's in factored form. Factored forms are nice because we've already dealt with them in quadratics. We're going to do the same thing. I can complete this graph. Let me kind of show you what this thing would look like as a where we would like to be able to go when we end this thing. Okay. First of all, this is, if I expanded this thing out, I'm not going to do it, but this would be a third degree right here. X cubed would be the highest power. X cubed times x would be a x to the fourth. Okay, so all I'm going to do is go down here and minus 2, x minus 5, x plus 1 cubed. And I would say, okay, here's, if I expanded this, this is going to be an x cubed plus a bunch of stuff. Then I'm going to multiply this by a x, so I'm going to have a fourth degree poly. This is understood 1. I can just count these up. This is going to be a third degree. This is going to be a first degree. Multiply this together, I get a fourth degree. Okay, my a to the n, so once I expanded this stuff, I'd have x to the fourth. I'd multiply that times a negative 2. So my leading term would look like minus 2x to the fourth, and then I'd have a bunch of other stuff. I don't even have to expand it out. Okay, this is going to give me the end behavior. Even degree, negative. Evens look like that, and then this is the negative. Okay, so I know I'm going to be coming from like this, and here we're just doing a quick sketch. Sorry. Coming here because it's a negative, and then going down again because it's negative. So if this was just an x to the fourth, it would go down here because of the negative 2. Okay. So out at the ends, this is what it's going to do. Now we can do other things with this right now. What about the y-intercept? F of 0 to get my y-intercept. Let me clean this up just a little bit. So f of 0 would be negative 2 times negative 5 times 1. This was a cubed times 1 cubed. Okay. 0 here, 0 here, negative 2 times negative 5, and plus 1 cubed is plus 1. So this would just be 10. Let me switch pens. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somewhere up here, that would be my y-intercept. I just wrote 0, 10, sorry. Okay, so that's my y-intercept. I'm coming from here. I need to get through here. This is a continuous function. I need to get up there from someplace. What do I need to find out where it's going to cross? Those are my zeros. Where's this thing 0? Okay. So where is this equal to 0? X minus 5 equal to 0. Solve x equal to 5. X plus 1 is equal to 0. The only time this is going to be 0, 0 cubed is the only time that thing is going to be 0. And that's at x equal to negative 1. This is a multiplicity 3, okay? And we're going to see what this is. So at x equal to 5, 1, 2, 3, 4, 5, I'm going to have my x-intercept, and then at negative 1, right there, okay? So I kind of do this thing out. It could be doing anything, but I'm going to kind of make a smooth curve through here. And my quick sketch would say here, here, this was where I'm coming down this way, and now I've got to go through. And what I'm going to do later on is say, if this is linear, I'm going to go straight through. If it's a square, I want to touch, And then if it's a cubed, I'm going to go through with that same little squiggly like that. And I kind of draw, okay? There's a lot of other stuff that could be going on, but this is going to be somewhat of the basic shape that at this point that we can tell. So if I go here, I'm going to bring up Desmos again, shoot this over to the side. Bring this up. And again, this is the local max. If I go, so I've got a local max that's way up there, okay? But we don't have the information. Later on, when we do calculus, we can know where these local max and local mins are. But this gives us a starting point that we're going to go here. This where it crosses the x-axis, that should be around 10. So right there, if I do, that's the 0, 10. And here's my 0, 0, and then note the end behavior, okay? So this gets us started with a graph of a polynomial. Here, we don't know the information unless we actually started graphing some pieces in here. We could improve the picture, but we're just going to do a rough sketch and get the necessary information and then do Desmos or pick extra points between those. Like I said, calculus, once you take calculus, you'll be able to pick this point, and that would give you another point up here to go through and then come back down. Okay. What did I say? Now here, I did this wrong. This was the -1 was the cube, the multiplicity. This should have been straight through, and this one was the one with the multiplicity 3. That's the picture that goes through here, like that, and then this would come straight through. Sorry. That's the straight through at the x equal to 5. The x equal to -1 is my multiplicity 3. I sometimes do this to make sure I've got these straight, and I didn't do it in this case. Okay. Okay, so we're just going to do the end behavior real quick, picking out the degree, the leading term, figuring out what that leading term is in this case. So for A, f of x, let me get my cursor out of the way, is -0.3 x to the 4th minus 5x squared minus 3x plus 4. Here is the leading term. That's the biggest term. This is the only thing I have to worry about. This is a 4th degree poly. We classified it, that would be classified as a 4th degree polynomial, okay? So the n is equal to 4, that's the highest power. This is even, okay? So if we started with that, it would be that kind of picture, up, up. Then we look at A, this is less than 0, so I'm just going to flip that. Now I'm going to write the end behavior. So from this one, as x goes to -infinity, I'm going this way. F of x goes to -infinity. And then for this one, both of these going to -infinity. Plus infinity, I'm moving this way. This is going to -infinity, looking down this way, looking down that way. Okay. And if I'm doing this one, if I'm doing g of x, okay, so this is kind of what I'm doing. I'm picturing if I expanded this thing out, I would have multiplied times x to the fourth. That's going to be the biggest stuff. I'm going to have other stuff in here. This x squared plus other stuff, and then a 3x and other stuff, the minus 5 in this case, okay? So here, if I multiplied these together, the biggest terms, this is where I would end up, 4th, 5th, 6th, 7. X to the 4th times x squared is x to the 6th. And then when I got around to multiplying this thing, as this would be 3x, 4, 5, 6, 7. Okay? And the only reason I kept this is in case this was negative, I would make sure this was negative. But here's a positive and positive. So this is equal to a positive x to the 7th. Okay? 7th degree poly, n is equal to 7. The basic thing that I'm going to work for odds is that x cubed. So here, as x goes to negative infinity, f of x goes to negative infinity. The bigger we go here, the bigger it goes negative. And as we go positive, this thing goes positive. So as x goes to plus infinity, f of x goes to positive infinity. Okay. And we're going to continue with this. Let's go. Identify zeros and multiplicities of zeros is our next kind of concept of where we're going to go. Okay, so basically what we're going to do is be able, anytime, so let me give you a basic definition. Our x-intercepts, anytime where the value that I put in for x and I get f of x is equal to 0, those are called the zeros. That's just something that we just do, okay? We've also called them roots if they're real solutions. And I'll loosely use that. What's the root? Well, it's a complex root, right? But those are the very same thing. The zeros are the roots. Where it passes the x-axis, if it's complex, then it really is not considered a root. You know, it doesn't cross the x-axis, okay? So here kind of ties these things together of, I've got a bunch of factors, okay? I've got a bunch of factors. So I have some function g of x. Let's say, and if I can factor it, and I've got x minus 3, let me go cubed, x minus 1 squared, and x plus 2, okay? This, so if I solve this, x equals 3 is the 0, okay? When I put 3 in here, this is 0, this is 2, 5, you know, but this 0 gets rid of everything and makes g of x equal to 0, okay? 0 with multiplicity, 3. I identify that 3 because it's going to determine the shape of where it goes through the axis. Here, x equals the 1 is the 0, and it's got a multiplicity of 2. And then this has a 0 at x equal to negative 2, and the multiplicity of this is just 1. That's that power, understood power, okay? What the multiplicities do is give you this. So anytime, this is just like that cubed over here, this picture. This is a cubic. I'm going to do the same shape when I do this thing. So I've got, what have I got? A 1, a negative 2. So let me draw just a quick axis here. Here's my y, here's my x. Negative 1, negative 2. Here's my negative 2. And then I've got a 1, and then 2, 3, 2, 3. Okay. So I've got a 0 there, a 0 there, a 0 there. Okay, here's my x equal to -2. Here's my x equal to 1. And here's my x equal to 3, 0. Okay. And what I like to do is go out here to keep it straight and say, well, this is the -2. What was its multiplicity? 1. Here was the x equal to 1. Multiplicity was 2. Okay. And then this one was 3. And the multiplicity was 3. Okay. And then I'm going to talk to you about each one. So if you have a first degree, you're always going to go straight through. So what does the end behavior look like? Let me put the end behavior in here. This is x cubed, so 3rd, 4th, 5th, 6th. So this is a 6th degree polynomial. Positive coefficient. This is going to be up, so I'm going to be going up like this, up like this. And this is going to tell me how I go through these zeros, okay? So I'm going to start from here. That multiplicity 1, I'm going to go straight through there, okay? I'm going to go through to the next one, so I need to get my y-intercept. My g of 0 is going to be -3 cubed, 0, just a -3, -1 squared, and then 2. So this is -27 times +1 times 2, -54. So way down here, break on my axis because I haven't got my scale large enough. I'm going to go through -54. And what I'm going to do, I have no zeros in here. The next thing I go from left to right is my y-axis. So this is going to go all the way down. It may do some other stuff here, but then I'm going to go back up to here. The m equal to 2 is going to be just like a quadratic. A second degree is just going to touch. Okay, so I need to come up here and just touch that, just like that. Okay. I need to end up here. I've got that other 0, so I'm on my way. That's a multiplicity 3. And now I know what a 3rd degree looks like as it's going through. It looks like that. So this is going to come in. And here I need to make that little sharp and then go up. And make sure I come up and then up that way. Okay. Now other things may be going on. This doesn't need to curve back over, but it was just me getting that one. Okay. So cleaning it up a little bit. Okay. Even multiplicities, just touch. That's what this is saying, okay? If a polynomial factor has a factor x minus c, this is a first degree, okay? It has, then c is a 0, multiplicity k, this is just 1, okay? If the c is a 0 of odd multiplicity, then the graph crosses. If it's 1, it's straight through. It crosses here at 3, but it does that little dip. And then if it's even, where this says right here, I just touch when I'm drawing my graph. So that's more information that I have to add in to my picture, okay? So for something, I have relative maximums. Here's a relative max, or somewhere this may not be a relative max. I would need a better picture. We can do that in calculus. We can determine where local maxes and local mins are. But these things where there is a local maximum or local minimums are called turning points, where I go from, positive, negative, negative, up or down, down, up, turning point, turning point, turning point. And here is a kind of a summary of this thing. It says the graph of a polynomial function of degree n has at most n minus 1 turning points. So if I ended up with too many zeros here, then I'm getting too many turns, okay? That's what that's saying. So if I have this 6th degree, I should have it at the most 5 turning points, okay? So here I see 1, 2, 3 turning points, and that matches. Now there may be some, if we graph it, there may be another little one out here, and we can't do that until we do calculus. So I'm going to do Desmos again. Let's see what the real thing looks like and see how much we can match up. I think I got it better if I just start over again. Y is equal to x minus 3 cubed. You see with that little piece right there, that goes through the 3. X minus 1 squared. Now if I open this up, you see just from those two pieces, the even touch at the 1, and then that little dip from the 3. And then finally we had x plus 2, and then that adds us that piece straight through because it's a first degree. And then if we go down here, we'll find that it crosses, I think, negative 54. So we'll run in there. Where's my 0? There's a 0, negative 54. That's my y-intercept. Okay. But notice I turned way down here, so I've got a turning point. That would be so that I didn't pick up unless I had calculus. So that would be an extra one down there, maybe. That would be the one that I counted there. Okay. So the 1, 2, the one down here is the 3, and there's a couple other that's hidden that we didn't see. Okay, but we picked up most of the elements here. And again, you could do some, if you needed a little more extra, you could pick out and actually calculate for -1. That would give us something down here. Halfway between these two would give you a better idea here. So you can improve upon this, but that's the basic information that you can get just from the analysis part of it. The rest of it, you're just going to have to calculate numbers to get a better picture. And again, later on in calculus, you're going to learn to find out where these local minimums and locals. This could be way down here, right? This could be way down here, and you would learn how to do that in calculus. Okay, so now let's go through and kind of pick out, well, from this one, I found the zeros by looking at the factors. Let's see if we can get in and do some factoring again. So we're back to factoring, but now we're going to have higher degree polynomials. And let's see if we can work those through. Okay. So I've got, let me put this over a little bit. So I've got f of x, 4x cubed, minus 4x squared, minus 25x plus 25, and I would like to get this factored. The first thing I'm going to check for if I've got x's when I'm dealing with that big of a polynomial, do I have x's in everything? If I have it in everything, I'm going to factor out the highest power to get it down to this form. Okay, so this I can't take out of x from everything. The next thing I want to try at this point is, can I get these two the very same type of factors? Okay, that's that factor by grouping. So I want to say 4, I can take out a 4 from here, 4x squared, and this would be just a x minus 1, okay? And then I want to see if there's anything that I can do to turn this thing into something that looks like a x minus 1. and I do that, I see that I can do that. This needs to be a negative. That's a negative, and it needs to be a positive. So I'm going to take out a negative. So now this is 25x minus 25. I'll write this up here. So I'd have a minus, but I need an x minus 1. Well, that's the same number, so I'm going to take out the 25. This does not work in practice a lot. It has to be kind of cooked up to be, to do that, but that's what, a lot of these are made for you to be able to factor and look at those, okay? So now notice that these two are the same. Here's a factor, here's a term, here's a term. I want to take out the x minus 1 from both of those terms. Now what am I left with? 4x squared. I pulled out the x minus 1 here, and then the minus 25. Okay, and now we look at this and see, is there anything I can do to factor that? And this looks like the form a something squared minus something squared. And what is this? This is like a squared minus b squared, but what is this? If I put this into this term, this is 2x squared, and that's 5 squared. 4x squared minus 5 squared, and now I get to factor a minus b, a plus b. 2x minus 5, 2x plus 5. So totally factored out, this thing now looks like x minus 1, 2x minus 5, 2x plus 5. And that's our function, factored. Okay, we got them linear factored, we're good. We're all the way down, all in multiplication. Okay, so I can do things like zeros. X minus 1 is equal to 0. So x is equal to 1. 1 is a 0. X is a 5 halves is 0. Solve that equal to 0. And then x is equal to negative 5 halves is a 0. The multiplicities are all 1s. M equal 1, M equal 1, M equal 1. So let's find the zeros of this one. To factor, here's that I've got an x in each one of these things, so I want to take that out. And then I want to go back and then try to factor whatever's left. I want them in terms of linear factors and higher multiplicities. I don't want to let this with a quadratic. Okay. 2 factors adds to this number to 10. 5 and 5 should be jump out at you. Those add to 10. X squared plus 5x plus 5x plus 25, and those two 5x's would give you the 10x. So this I would write as x plus 5 squared. So this x is equal to 0 at x equal to 0. And then, so that's one of my zeros. X equal to negative 5. X plus 5 is equal to 0. And this is a multiplicity of 2. So when I drew the graph, this would go straight through. This would just touch the x-axis. Okay, so here's some more practice for you. Here's an example. What effect do the multiplicity of the zeros have on the graph? Okay, so here I have 3, x equal to 0, x equal to 1, x is equal to -3. The multiplicity is the one I draw it straight through, no curves, no dips, no touches, all straight through. Here is, I've got x equal to 0, straight through, x equal to -3, straight through, multiplicity 1, multiplicity 1. Here at x equal to 1, I've got a multiplicity 2, the graph just touches. X equal to 0, straight through, x equal to 1, straight through, x equal to -3, I touch because the multiplicity is 2. Okay, so I'll let you look at these things. Give the maximum number of turning points. So here I would identify the degree of the polynomial. This is a third degree polynomial. The maximum number that I would have was 2 turning points. Here's a turning point, my local max. Here's one, local min. 2 is less than 3. That's what I would expect. I would not expect another. It has to be n minus 1, the maximum of 2. I may not always see this, but if it's a nice pretty graph and expanded out, you know, you would see these things, and that would be it. So here's what we're going to do, the basic game plan for sketching polynomials, if we can get it. Now, a lot of these are with integers, integer coefficients. We can factor them if we have irrational. So if I have a pi in here, you know, decimal numbers, it gets to be a little strange. Sometimes we can, sometimes we can't, okay? But the ones that we're going to do, we're going to basically identify these things. We're going to use the leading term to determine the end behavior of the graph. The leading term is the dominant term. That's the biggest thing that's going to, at the very end, it's going to dominate the behavior. We're going to check for y-intercepts. This is always going to be in a polynomial. The polynomial is always going to go left to right and somewhere across that y-axis. Polynomials do not have to have x-intercepts. You can have this thing doing all kinds of stuff like this. Or all down here like this. Okay, so I can have all of this stuff, no zeros. Okay, but I'm always going to have a y-intercept, or I did this one. Let's do this like this, y-intercept. I'm always going to have a y-intercept on a poly. Okay, so the next step I'm going to do, try to factor this thing, or if it's in factored form, all I'm going to do is evaluate the zeros, evaluate for zeros, and note their multiplicities along. Okay, so once I kind of do, here's my 0, here's my 0, here's my 0, I want to go back and note degrees, you know, m is equal to 1. So for this one, if it was a multiplicity 2, it would look like that. Here or here, you know, this one looks, it's a little different, but it's either coming here or it's either coming from there. This one's touching that way, and then m is equal to 1 is either going to be straight through this way or straight through this way. But we always have to know in behavior to want to know what this thing is going to do at the outside. Okay. We've got to start from this. I start from left to right, start from this end behavior, whichever one I'm going to do, and then I start going through zeros, the y-intercepts, making sure I do the right multiplicities to get me where I need to go. Okay. And this is basically what I was going to do. Sometimes you can test for symmetry, helps you out. If you've got the even symmetric to the y-axis, does f of negative x equal to f of x? And then the odd functions, then you can get and say, okay, this is an odd function. I'm just going to do exactly what I did over here. Okay. Odd is here symmetric with respect to the origin, and then an even function, I get to just fold it back over. Okay. Okay, again, if you need greater level of accuracy, then I just need to find some, a couple of different points within those zeros or outside those intervals and then plot them out. Okay, so here kind of finishes this up. So sketch the function. It's given us in factored form. Okay, so I'm going to write down my zeros. X is equal to 1, my zeros. X equal to 1, the multiplicity is 2. X minus 1 is equal to 0. X plus 3 is equal to 0 at x equal to negative 3. Multiplicity is 1. And then x minus 4 is equal to 0 at x equal to 4. Multiplicity is 1. Okay. F of 0, negative 1 squared is plus 1. 3 times negative 4 is negative 12. Okay. These are the zeros. That's the y-intercept. I just stuck 0 in here and said negative 1 squared. Well, that's plus 1. I don't have to worry about it. Plus 3 minus 4, then negative 12. In behavior, this is a second, third, fourth degree poly. Second, x squared times x cubed times the x is x to the fourth. So fourth degree poly, n is equal to 4, even, positive coefficient, a greater than 0. So the in behavior, so I'm going to start out, and I'm going to kind of refine this thing as I go. Okay. So even is going to be up, just like if I did the even x squared up. Okay, that's a starting point. And then I do my scale, and I'm going to bring these in as I need it. Okay, from left to right, I've got a negative 3. That's that one. My multiplicity is 2. Okay, so when I come here, I'm not going to go through the x-axis. I'm just going to touch it and go back up. I'm sorry, x is equal to negative 3. That was my 1. It is going to go through, sorry. Okay. So at x equal to 1, then I have my multiplicity is 2. Then I'm going to touch from wherever I did. So this is going to go straight through, and then I'm just going to touch and go back down. And then I've got my x equal to 4. And then I've got a multiplicity of 1, and then I go through. And then down here, my y-intercept, I'm going to go all the way down to the bottom, and this is my negative 12. So then I just kind of use what I know, okay? So I've got an m is equal to 1. I'm going to come back from up here. Depends on how sharp it is. I try to do a smooth and kind of go through here. So I'm going to go through, straight through because the multiplicity is 1. I go through here. This may come down and then back up, but I just use that as my point. I'm going to come back up. Multiplicity is 2 as I'm going to touch. Go back down, and then I've eventually got to go back here, so I got to come back up, and then I go out like that. And then if I needed more accuracy, I would just evaluate this at negative 2. Bring this down. At negative 2, negative 1, plot some points, and then finish filling that out. Okay. So if we did this real quick, I'm going to go back up here, get rid of this. My y is equal to my x minus 1. Squared times x plus 3 times x minus 4. And here straight through, it's going to open this up a little bit from right here. Straight through, just touch because the multiplicity 2 and then the multiplicity 1 goes straight back through. Okay. And here, this went way down, so this I would have needed to apply to -2, -1, get these values to get a better picture of this. But right here, what did we say, the -12? Hold on, let me get up here. Right here is the 0, -12. That's my y-intercept. This comes down much sharper than what I did. And again, calculus will be able to give us these 2 points. Later on, we're going to learn how to do that. We're going to find that the slope is 0 where it changes. We're going to do something similar to that difference quotient, that slope, and do here's a 0, here's a slope changing. Here's a slope of 0. We'll be able to identify those x's and those values and plot those as well. So the intermediate value theorem, it just says if I've got, for a continuous function, polynomials are, and this applies to a polynomial, let f be a polynomial function. If I've got 2 values where f of x is positive, greater than 0, these are all positive stuff up here, negative stuff down here. And if I've got another value where f of x is the opposite signs, so these two are opposite signs, the only way with a continuous function that I can get from positive to negative is go through the x-axis or a 0. Okay, that's what that is. It just says that if you've got here, then on this interval, it's changed sign between here and here. That's the interval. It's changed sign, then I've got to get through the x-axis to get that. That's the intermediate value theorem, and it's used in a couple of different places to help prove things. We don't really use it. We just say it's a polynomial function. Here's the 0. We're either going to touch, cross. Okay, so this was show that f of x has a 0 on this interval. So if you're doing a graphics calculator or something, let me drag this over a little bit. Sometimes numerical solvers use this principle of saying, I've got some function and I know where it changes sign. What I'm going to do is just kind of narrow this interval down, keep checking when it's going to change signs and keep switching, and then narrow down where the 0 is, okay? So the intermediate value theorem said if this thing changed sign on this, then there's a 0. So you're just going to evaluate it at each one. Is there a 0 on -1, 0? Closed interval. So I'm going to evaluate it f of equal to -1. This is going to be -1 cubed minus 13, 1 squared, -1, sorry. Plus 33 times -1 plus 35. So this is -1, -1 squared. So this is going to be minus 13, minus 33, plus 35. And now I'm not going to do the actual value. I'm just going to note that this is bigger than 35, so the sign is negative. Okay. And what about f of 0? 0 cubed minus 13, 0 squared, plus 33, 0 plus 35. All of these are 0 because the 0, 0, 0. And the sign on this is just the positive. So I've gone between a negative. So here's my -1. Here's my 0. I've gone from a negative value to a positive value. So I've got to have a 0 in that interval. And that's the intermediate value theorem.